In this lecture, example of metric space part 3, I give some more example on metric space. So one by one consider here. The first example is show that the function d defined by d of sequence xn sequence yn is equal to summation of xn minus yn bracket square n is equal to 1 to infinity raised to 1 half, means we are taking the under root of this. Now, this sequence xn yn belongs to L2, is a metric on L2. Means we have to show that this D defined on the elements of L2 is a metric. So, what is a L2? So, L2 means the set of all sequences L2 be the set of all sequence x is equal to sequence xn, n is equal to 1 to infinity of real numbers. Now, this satisfies the condition that summation of xn square n is equal to 1 to infinity is finite. So, this is a L2. So, it contains the sequence xn n is equal to 120 of all real numbers which satisfy this condition. Now, we have to show that this D is a metric on this L2. So, consider the three elements. X is equal to sequence xn, y is equal to sequence yn, z is equal to sequence zn belongs to the L2. The first condition, that is the consider D of xy. It by definition of D, it takes value summation of xn yn bracket square n is equal to 1 to infinity raised to 1 half. Now, this xn minus yn bracket square is a positive. We take the summation of all positive terms. So, this must be the positive, and under root of positive is again a positive. So, therefore, this must be the positive, and therefore, it satisfies the non-negativity. Now, next, that is the coincidence. So, consider D of xy is equal to 0. So, putting the value of D of xy is here, and now taking square of both sides. So, 0 square is 0, and we get this value. Now, here summation of all square value is equal to 0. So, therefore, individual square value must be the 0. From that, we get the x1 is equal to y1 is equal to 0, x2 minus y2 equal to 0, and so on. So, we get x1 is equal to y2, x2 is equal to y2, x3 is equal to y3, and so on. So, therefore, we get the sequence xn is equal to sequence yn, and sequence xn we consider the x, and sequence yn we consider the y. So, if we consider D of xy is equal to 0, it implies we get the x is equal to y. And if you consider the x is equal to y, by implies and implies by, we get D of xy is equal to 0, and therefore D is a coincidence. Now, next, that is the symmetry. So, consider D of xy, putting the value of D. Now, here we have to, in place of xn yn bracket square, take as a yn xn bracket square. So, the value is not changed because the xn minus yn square is same value as yn minus xn square. But this is nothing but the D of yx, and therefore it is a symmetry. Now, next, triangle inequality. So, consider the D of xy is equal to, putting the value of D of xy. Now here we have to add and subtract Zn. Now xn minus Zn, put the value of an, and Zn minus yn, put the value bn. We get this value. Now using the Minkowski's inequality that explain in example of matrix space part 2, we get this is greater than equal to summation of an square, n is equal to 1 to infinity raised to 1 half, plus summation of bn square, n is equal to 1 to infinity raised to 1 half. Now by back substituting, that is the putting the value of an and bn, we get this. Now this is nothing but the d of xz, and this is a d of zy, and therefore it satisfies the triangle inequality. Therefore D is a metric, and therefore L to D is a metric space. Now this metric space is known as a Hilbert space. Now the next example, prove that the C of closed interval a to b means consisting of all real valued continuous function, meaning of this C of closed a to b, with the function d defined by d of fg is equal to integration of f of x minus g of x bracket square dx, x running from a to b raised to 1 half. Here a is less than b. So we have to prove this D is a metric space. So one by one we have to prove all the 4 properties. So first is a non-negativity. So consider d of fg. Putting the value of d of fg is here is now here f of x minus g of x square. So this is a positive. So we get the integration of positive terms, and here also a is less than b. So therefore this must be the integration must be the positive, and under root of positive we get the positive, and therefore d of fg is positive. So greater than equal to 0. So therefore it satisfies the non-negativity. Now the coincidence. Consider d of fg is equal to 0. It implies by we get putting the value of d of fg is here and equal to 0. Now taking the square of both sides, we get the 0 square is 0, and here we get this value. But here a is less than b, and integration of f of x minus g of x bracket square dx, x running from a to b is equal to 0. So therefore we must have f of x minus g of x bracket square is equal to 0. From that we get the f of x minus g of x is equal to 0. It implies by we get the f equal to g. So therefore it satisfies the coincidence. Now next, symmetry. Consider d of fg is equal to, by definition we get this value. Now here substituting the f of x minus g of x as a g of x minus f of x, because the value of f of x minus g of x square is same as g of x minus f of x square, but this is nothing but the d of gf, and therefore it satisfies the property of symmetry. Now next we have to prove the triangle inequality. For that, here consider d of fh plus d of hg bracket square. Now if you taking the square of this, we get value of d of fg substituting here, and value of d of hg is here. So we're taking the square of this. Now this is the first term plus another term bracket square. So using the formula, that is the a plus b bracket square is equal to a square plus b square plus 2ab, we get value of this is a square plus b square plus 2ab. Now this value taking as it is, this is also as it is, but here in place of this value we have to taking integration of f of x minus h of x into h of x minus g of x dx, x running from a to b. Why? Because this formula we get the value of this is nothing but the this, but here is equal, and so we get the less than equal to. Now this is nothing but the f of x minus h of x plus h of x minus g of x bracket square dx, x running from a to b. Now h of x gets cancelled. We get integration of f of x minus g of x bracket square dx, x running from a to b. So now therefore we get, taking the square root of the both sides, we get this value, but this is nothing but the d of fh, and this is a d of hg is less than equal to value of this is by definition of d of fg. So therefore it satisfies the triangle inequality, and therefore d is a metric. On the next lecture we have take some more examples on metric space.